everybody, welcome to Unit 3, Lesson 6 and 7 about similarity and transformations. Here's our learning targets. I can write similarity statements. I know the definition of similarity, and I know the relationship between corresponding sides and angles in similar triangles. Okay? If you haven't already done so, please take a moment and open up the linked Desmos activity so you can try some of this stuff along with me. Better learning that way, okay? Speaking of, I want you to pause right now and do slides 1 through 4. Oh, you're back already. That was fast. Okay, so here's what I came up with. On slide 2, why is ABCD not a dilation? Well, the first one's a square and the second one's a rectangle, right? So obviously, if your original shape has all of the sides really close to the same, when you dilate it, all the sides should be really close to the same still, okay? Because everything gets multiplied by the same number, the same scale factor in a dilation. And that didn't happen here, clearly. The other thing that I would reference is that, hey, with a dilation, every line that goes through the image point and the original point should meet back at your center of dilation. But if you look at the line that goes through what are, supposedly, the original point C and the original point or image point F, same with B and E, those don't all meet back at P. So that can't be a dilation. That's not right. Next, on page 3, what are the scale factors? Well, to go from the big triangle F to the little triangle G, that would be a scale factor of 3/4. And to go the other direction, it would be a scale factor of 4/3. If you're not sure how to find that, I think this way. Okay, I know that 4 times something would give me 3 if I was moving in this direction. And then you could solve that using basic algebra by dividing both sides by 4. So to go from the big triangle to little triangle, scale factor of 3/4. Same process to go the other direction. What I would mention is interesting about these two numbers is that they're reciprocals. They're reciprocals. The same numbers for the fraction, just the numerator and the denominator get flipped. This won't be obvious if you just have them written as decimals. So just throwing that out there. If you want to see this relationship, you got to have scale factors as fractions. Lastly, before we move on, what is the scale factor from here to here? It's 3/2, or 1.5. 4 times 1.5 gives you 6. Okay. On the next page, it asks you to describe the transformations it would take to go from triangle ABC to triangle DEF. All right. Now, think about this in terms of what we did with congruence. What kind of transformations did we do with congruence in order to make one shape land perfectly on top of the other? Now we get to add dilations to our inventory of things that we can do. Again, I will say pause this and try it out. What sorts of things would you need to do to make one shape land on top of the other? Here's my answer. So I would start by translating triangle ABC by the vector from B to D. I know that those 2 points belong together, right? B has to end up where D is. So let me try that right now using my transformation tools. I will, spoilers. Well, it's all written out there. Anyway, here's my translation from B to D, boosh. Okay, so now I have 1 point in the right place. After that, I'm going to rotate around point D, rotating around D so that, that point stays where it belongs until A lands on segment DE, which is 21 degrees in this case. And then lastly, I'm going to dilate it by a scale factor of 1.5 so that the length of that segment that's 4 changes into a segment of length 6, and that makes it so that all of the points are coinciding, which is a cool thing to do. This is what it means for figures to be similar, by the way. Definition on page 6. One figure is similar to another if there is a sequence of rigid motions and dilations that takes the first figure so that it fits exactly over the second. Notice that that's close to our definition of congruence. If figures are congruent, then there's a sequence of rigid motions that takes one figure exactly over the second. But with I guess, similar figures, you also get to throw dilations into the mix because they can be getting bigger or smaller at a proportional rate. Okay. So with that in mind, kind of the old rectangle is a square, square is a rectangle conundrum. I want you to answer the questions on page 7 and 8 based on your understanding of what I just said there. Okay, here's what I said. Congruent figures are similar all the time. That's every single congruent figure is also similar, because congruence means that there is rigid transformations that takes one figure and makes it fit exactly over the second, which is darn near close to the definition of similar, except it doesn't say anything about dilations. Okay, well, to be similar, if you throw in a dilation of, say, 1, okay, then yeah, the scale factor is 1, and the shapes still have the same corresponding side lengths, and so that's both congruent and similar. Okay, uh, similar reasoning for the second one, except for I would say it could be true, although most of the time it won't be, because similar figures don't have to have a scale factor of 1. It could be a scale factor of any number, which will make it bigger or smaller most of the time, and then it's not congruent. But if the scale factor is 1, then it meets both of those conditions. Okay, so on this next slide, I'm going to pause here and I'm going to find some ratios, and I recommend that you do the same before we move on. Okay, I filled in my table, and perhaps not surprisingly, we ended up with a whole bunch of ratios that were the same. So that seems like a good indicator that these shapes could be well on their way to being similar. Also notice that the scale factors for the big shape divided by the little shape, or the little shape divided by the big shape, those are reciprocals of one another, 2/5 or 5/2, if you change the scale factors into fractions. How about that? I want you to pause again and try and tell me what sort of transformations it would take to fit one of these shapes onto the others. Think about what we did on our other example, if that helps at all. Okay, here's my sequence. So first we translate triangle ABC using the vector from A to Q. So that would put A on top of Q. And also, I don't need to do any rotation here because it already tells me that AB is parallel to QR. So I know that when we shrink the triangle down, I don't need to do any rotation. It'll just have B on top of R at that point, because AB will be the same length as QR, and likewise EA will be the same length as TQ after we do a dilation by 0.4. Okay, neat. What I say after that? So, in general, when two shapes were congruent, we had that congruence symbol, and we would write congruence statements. We can do the same thing with triangles and similarity statements. Just use a different symbol. The order is still important to me, though. And so I would say, as one possible example, triangle ABE is similar to triangle QRT. Notice that all of the correct matching angles are in the same order. First A, then B, then E, and in the same order, Q, then R, then T. Okay? So on the next page, Marvin does it wrong. Okay, Marvin says that triangle EAB is similar to triangle QRT. That's wrong, Marvin. Those points are in the wrong order. Okay, here's the order that they should be in, right? E matches up with T, A matches up with Q, B matches up with R. So EAB is similar to TQR. Sorry, Marvin. I got a little too excited there. Okay. So here is another definition sort of deal. If two triangles have all pairs of corresponding angles congruent and all pairs of side lengths in the same proportion, then the two triangles must be similar. That's a theorem. It means that you can guarantee that they would fit on top of one another with rigid transformations and dilations if all of the sides are proportional and all of the corresponding angles are congruent. So let's try and apply that definition. Okay, do the triangles on page 14 and 15 meet those conditions to be similar? Why don't you take a moment to consider, and then I'll talk about it again. Okay, short version. Yes, this pair of triangles is similar because all of the angles are marked as being congruent. Those little arc markings in the corner tell me so. And if you match up all of the corresponding sides, like shortest side XY with shortest side RQ, there's a scale factor of 1.2 there if you go from the smaller triangle to the bigger triangle. And likewise, if you do the same thing with the two big sides and the two medium sides, it's always the same scale factor, meaning that all of the corresponding angles are congruent and all of the corresponding sides are proportional. So yes, these triangles are similar. The same could be said on this last page for triangle ABC and triangle ADE. Now, it might throw some people off, because if you just look at, say, like 4 to 16, like some people might say, well, that's a scale factor of 4, Mr. Martin, and 5 to 15, that's a scale factor of 3. But remember that it's important to keep in mind, when you're checking for proportionality, you need to use the entire sides of the triangle. Okay, EC 15 is not a side of triangle ABC. Okay, the whole side is 20 long, and so if you compare 5 to 20, yeah, that's times 4, just like 3 to 12 is times 4 for side AD and side AB. Okay. So again, all the corresponding angles are congruent and all of the corresponding sides are proportional. Oh, I kind of glossed over these angles right here. How do I know that these angles are the same? Well, that would be related to our discussion from section 3.5 about how if you can show that there are proportional sides, then that means that a dilation has occurred. And if there's a dilation going on, then we know that dilations create parallel lines. So DE is parallel to BC, and therefore the angles that I've listed there are corresponding angles in those triangles and must be congruent. If you're interested in some text versions of a summary, I'd say check this out. And then also there's this thing right here. But otherwise, look forward to hearing some more about these similar things in class.